For decades, Pluto has been a world shrouded in mystery, a ghost planet wandering at the edge of sunlight. It's the lonely outpost of our solar system, frozen, forgotten, and endlessly distant. When NASA's New Horizons spacecraft swept past it in 2015, humanity gasped. For the first time, we saw the face of a world that had existed only as a pixel for generations. Rugged mountains of water ice, glaciers of frozen nitrogen, plains that gleamed like glass under the dim rays of the sun. Pluto wasn't dead. It was quietly alive in its own alien way. But something in that data didn't fit. Something that NASA didn't explain. Instruments measuring Pluto's upper atmosphere showed temperatures nearly 30 degrees colder than every model predicted. The math refused to work. Scientists expected about minus 73 degrees Celsius, but readings dropped below minus 100 degrees Celsius. That's not a small mistake. That's a cosmic anomaly. Something was draining heat from Pluto's atmosphere, stealing energy faster than physics allowed. Inside NASA, the anomaly was treated like a whisper, real, but best not spoken aloud. The agency had already battled the controversy of Pluto's planetary status. Another mystery would only draw public speculation. Yet, among planetary scientists, the puzzle lingered like static at the edge of a radio signal. Where was the missing heat going? The more they studied the numbers, the stranger they became. There were fluctuations, rhythmic, repeating every few days, as if the cooling were pulsing in time with something deeper inside the planet. Some called it coincidence. Others quietly archived the data and moved on. But for a few, the mystery became an obsession. Those who dared to ask deeper questions noticed odd patterns buried in the telemetry, faint electromagnetic spikes near the terminator line, the boundary between day and night. They were too weak to be confirmed, too strange to ignore. It was as if Pluto's chill wasn't random, but part of a cycle, a pattern written into its orbit itself. The numbers didn't just defy physics, they hinted at intention. For nearly a decade, the question went unanswered. Pluto became an enigma, shelved in silence, dismissed as unsolved cooling. But now, the world's most powerful eye, the James Webb Space Telescope, has turned its gaze toward that frozen world. What it found is rewriting everything we thought we knew about Pluto, because what was cooling it might not be natural at all. When New Horizons made its historic flyby, scientists expected a cratered husk, maybe a few patches of ice, nothing more. What they got instead looked like a miniature Earth sculpted from alien stone. Towering mountains made of solid water rose like frozen fortresses, and vast plains of nitrogen stretched for hundreds of kilometers, smooth, hauntingly beautiful, eerily young. Pluto's surface wasn't static. It was active, shifting and reshaping itself in a slow geological ballet billions of miles from warmth. The spacecraft's instruments revealed delicate ripples etched across the ice, signs of convection, movement. That discovery alone hinted that heat still lingered deep inside, enough to churn its surface like slow lava beneath a glacial sea. To find internal motion so far from the sun defied every prediction of planetary physics. Yet above this strange landscape floated something even more unexpected, a thin bluish haze. It wrapped around the planet like silk, faint but luminous, visible even from space. It climbed hundreds of kilometers above the surface, layered in delicate bands that shimmered whenever sunlight struck. The haze wasn't supposed to exist. Pluto's gravity was too weak, its atmosphere too thin. But there it was, encircling the world in a ghostly halo. From certain angles, it scattered sunlight in shades of violet and sapphire, making Pluto look almost alive, as if breathing a soft radiance into the void. Photographs taken by New Horizons captivated the world, but for scientists, beauty gave way to confusion. When they calculated the thermal balance, the numbers refused to behave. The atmosphere wasn't just cold, it was impossibly cold, even for a dwarf planet on the solar system's fringe. Nitrogen and methane alone couldn't account for such rapid cooling. Something unseen was stealing heat faster than equations allowed. Teams re-examined every variable: solar flux, radiative transfer, instrument drift. They cross-checked against Voyager, Cassini, even early Hubble observations. Nothing fixed the gap. The data seemed to mock them, whispering that something fundamental about Pluto's atmosphere was misunderstood. One peculiar image showed faint concentric layers stretching higher than any model predicted, like ripples in an unseen ocean of air. It suggested the haze wasn't still. It was moving, expanding and contracting, breathing in rhythm with the planet's spin. If true, Pluto's atmosphere was more alive than dead, a dynamic, pulsating shell of matter behaving as though it had a will of its own. The discovery left scientists with an uncomfortable truth. Pluto's sky was breaking the rules. Above its frozen heart floated a mystery, elegant, silent, and colder than physics itself. 2 years later, one scientist dared to ask the question no one else would. Dr. Shi Jiang, a planetary physicist at the University of California, Santa Cruz, proposed that Pluto's haze wasn't passive. It wasn't simply floating dust. It was active chemistry, a living, breathing system on a molecular level, a planetary mechanism capable of regulating temperature. Jiang theorized that the tiny solid particles suspended in Pluto's upper atmosphere could absorb ultraviolet light from the sun and re-emit it as mid-infrared radiation. Normally, that process would warm a planet, trapping heat like a greenhouse. But on Pluto, distance changed everything. The converted energy escaped into space faster than it was produced, turning the haze into a global coolant, a radiative engine bleeding heat away from the sky. The proposal split the scientific community. How could microscopic grains dominate an entire atmosphere's climate? The physics seemed outrageous, but Jiang ran the numbers again and again, publishing detailed models that showed it was theoretically possible if the particles were abundant and complex, if they were more like soot than snow. At conferences, colleagues dismissed the idea as poetic science. One reviewer even wrote, "A planet cannot be cooled by its own dust." Yet Jiang persisted, driven by a conviction that Pluto's haze wasn't a byproduct, it was a process. He staked his career on one testable prediction. If he was right, Pluto's haze would emit a faint but measurable glow in the mid-infrared range between 15 and 25 microns. It would be too weak for any telescope then in existence. Only a future instrument with unmatched sensitivity could prove him right. That instrument was still a collection of parts and ambitions: the James Webb Space Telescope. Jiang's paper quietly ended with a single line that, in hindsight, reads like prophecy. Future infrared observatories may reveal the radiative heartbeat of Pluto. Then he waited. Months turned into years. Funding cycles passed. The world forgot about Pluto's cold anomaly, filing it under open questions. But Jiang didn't. He kept refining his models, certain that someday when Webb opened its golden mirrors, the truth would finally emerge from the dark. In May 2023, the James Webb Space Telescope was finally ready. From its orbit a million miles beyond Earth's atmosphere, it turned its instruments toward the farthest frontier, Pluto and its moon Charon. Using its mid-infrared instrument, MIRI, Webb could do something no other telescope could: separate the delicate heat signatures of both worlds. Engineers spent weeks calibrating the observation. At such faint levels, even stray warmth from the telescope itself could drown out Pluto's whisper. Then, as the first light reached Webb's mirrors, the data began to flow, and something extraordinary appeared. For the first time, scientists isolated Pluto's own thermal glow, filtering out Charon's contribution. Webb scanned across infrared wavelengths, 15, 18, 21, and 25 microns. And the patterns that emerged stunned everyone. Pluto's infrared signature was far too strong. The heat wasn't coming from the frozen surface. It was rising from above it, a diffuse glow in the upper atmosphere. The team subtracted every known variable: sunlight, surface emission, cosmic background. What remained matched the curve of Jiang's 6-year-old prediction almost perfectly. The haze wasn't inert. It was radiating. Energy streamed away from Pluto in faint waves, a slow exhale into the void. The missing warmth from 2015 had finally been found, escaping not through the ground, but through the sky itself. The discovery rippled through the astrophysics community. Jiang's impossible theory was vindicated. For the first time, humanity had proof that a planet's climate could be governed by solid particles suspended in air, by dust that behaved like an intelligent system. Scientists began to whisper about chemical feedback loops, about atmospheres that think. For decades, planetary climate had been the realm of gases: carbon dioxide warming Venus, methane sculpting Titan, nitrogen shaping Earth. But on Pluto, matter had rewritten the laws of climate. The smallest particles had claimed the power of worlds. Pluto had become the first world where dust, not gas, governed the air. These particles, tholins, were microscopic tar-like compounds formed when sunlight bombarded methane, triggering chemical reactions that built long hydrocarbon chains. Under Webb's eye, they appeared as fragile, oily fragments drifting in slow motion, glowing faintly in infrared like embers caught in a frozen storm. Tholins were unlike anything seen on Earth. They didn't just absorb sunlight, they managed it. By converting ultraviolet energy into heat and radiating it outward, they effectively created a planet-wide thermal shield, cooling the world from above. The realization turned Pluto from a frozen relic into a living laboratory of atmospheric chemistry. The haze wasn't random dust. It was an engine, a feedback loop that formed when ultraviolet light struck methane, producing haze that cooled the air, allowing more methane to condense, which then produced even more haze. Pluto's entire sky functioned like a self-tuning thermostat operating in slow motion. Every few centuries, as its orbit stretched closer or farther from the sun, the process renewed. The haze would thicken, collapse, then rebuild, maintaining an equilibrium that had persisted for billions of years. Webb's instruments even captured hints of vertical layering, strata of haze that glowed at different temperatures, suggesting multiple chemical regimes stacked atop one another like the layers of a cosmic onion. The complexity rivaled anything seen on Titan or even Earth, and Pluto wasn't acting alone. Webb found that methane escaping from its upper atmosphere drifted outward and fell onto Charon, coating its poles with red organic residue. The same tholins that cooled Pluto were painting its moon, transforming it into a living mirror. Scientists began calling the pair a chemical binary, two worlds linked by invisible threads of shared matter. For the first time, we could see that planets and moons might co-evolve through chemistry alone. In that single discovery, planetary science had to rewrite its rules. Climate, chemistry, and perhaps even life itself suddenly seemed less mechanical and infinitely more creative. The success of Webb's Pluto observations set off a cascade of new investigations. If Pluto's haze could control its temperature, what about other icy bodies? The first target was Titan, Saturn's massive moon, a world already cloaked in a thick orange mist of hydrocarbons. Titan had always been a favorite for astrobiologists. It has rivers of liquid methane, vast polar lakes, and an atmosphere thicker than Earth's. But when Webb turned its gaze toward Titan's edge, it found something startlingly familiar. The same mid-infrared wavelengths that glowed from Pluto's haze now appeared in Titan's spectrum, only stronger. Titan's haze wasn't just orange smoke, it was a living chemical engine, radiating energy into space with the same efficiency as Pluto's mysterious atmosphere. Webb captured faint oscillations in Titan's light curves that mirrored the rhythms seen around Pluto, suggesting a shared process, a cosmic pattern linking worlds billions of miles apart. Then came Triton, Neptune's captured moon, long thought to be geologically dead. Webb's data revealed faint, rhythmic emissions from its nitrogen atmosphere, a whisper of the same cooling mechanism operating in the darkness beyond Neptune. Even Triton's surface, once thought inert, shimmered with low-level heat anomalies hinting at active chemistry below the ice. Across the solar system, these distant worlds seemed to be speaking the same chemical language. The same balance of light, heat, and haze repeated again and again, like a code written into creation itself. Researchers began calling it the mirror effect. The idea that the outer solar system operates under a shared atmospheric rhythm, each world reflecting the behavior of the others like cosmic siblings. At the edge of sunlight, the frozen planets were no longer silent. They were alive in a new way, their skies communicating through invisible radiation, their chemistry echoing across space, and their very atmospheres performing a quiet conversation in the language of light. Under Webb's deep field spectroscopy, the haze over Pluto began to reveal its true complexity. Each wavelength carried the fingerprint of molecules never seen before in such abundance. Long carbon chains, nitriles, and compounds containing both nitrogen and oxygen bonds, the same elements that form amino acids, the building blocks of life. On Earth, these same reactions occur in our upper atmosphere when sunlight hits methane. Billions of years ago, similar chemistry may have sparked the first stirrings of biology. Webb's discovery hinted that Pluto's skies might be doing something comparable, a slow-motion simulation of prebiotic chemistry on a planetary scale. Dr. Tanguy Bertrand of NASA called it photochemistry that mimics the origins of life. The phrase stuck because it captured the enormity of what Webb had found. Pluto's haze wasn't just cooling the planet, it was cooking chemistry, recycling atoms into more complex forms. Generation after generation, the frozen world had become a natural reactor, creating the kind of organic material that might one day seed life itself. Then came a stranger revelation. When Webb measured how these particles absorbed and emitted infrared light, it detected a repeating rhythm, a pulse. Every 6.5 days, perfectly matching Pluto's rotation, the haze brightened and dimmed. The cycle was too precise to be random, suggesting a synchronization between Pluto's rotation, sunlight, and chemical activity. Further analysis revealed that the energy output of the haze fluctuated like a beating heart, as if the entire atmosphere was breathing. Some scientists compared it to photosynthesis, a primitive, planet-wide metabolism driven not by biology, but by chemistry. Others went further, suggesting it might represent the threshold between life and matter, a stage of self-organizing complexity that doesn't quite fit into either category. Suddenly, the border between chemistry and life didn't look so clear. The haze seemed to breathe, to change in harmony with the sun. Pluto, once thought dead, was pulsing like something awake, a sleeping embryo of biology on a world too cold to be alive, yet too complex to be truly dead. Once Webb had confirmed Pluto's living haze, the next logical step was to look beyond the solar system. Astronomers began scanning exoplanets orbiting faint red dwarfs, searching for similar mid-infrared signatures. The results were almost unbelievable. Planets like K2-18b, TOI 700d, and even GJ1214b exhibited the same faint dips at identical wavelengths, the same thermal fingerprints as Pluto's haze. These were worlds far larger, far warmer, yet somehow governed by the same mysterious chemistry. Their skies glowed with faint mid-infrared emissions, suggesting active, self-cooling mechanisms in their upper atmospheres. At first, the data seemed like coincidence, but the spectral alignment was too precise. Each of these planets showed signs of an infrared cooling cycle, stabilizing their atmospheres against stellar radiation. That stability meant something profound: habitability. Instead of chaotic worlds scorched by their stars, these planets might maintain mild, temperate environments beneath hazy skies. The same Tholen-like compounds protecting Pluto could be shielding these exoplanets, creating self-regulating climates where life might quietly emerge. Researchers noticed a deeper pattern. The strength of the haze correlated with a planet's orbital distance and stellar type, implying a universal mechanism, an invisible thermostat woven into the chemistry of the cosmos. The haze wasn't just an atmospheric feature, it was a cosmic principle, a system of balance embedded in nature itself. This redefined what it meant for a world to be habitable. Life might not need oceans or sunlight. It might begin in the dark, nurtured by haze that cools, shields, and evolves. In conferences that year, a new theory emerged, the haze hypothesis. It suggested that hazy atmospheres might be the incubators of life across the galaxy, protecting fragile chemistry long enough for biology to take its first breath. Webb's infrared data gave that theory its first proof. The James Webb Telescope had expanded humanity's imagination. Maybe the blueprint for life didn't start on Earth at all. Maybe it began everywhere the haze exists, on frozen moons, in distant exoplanets, in the quiet shadows where chemistry learns to dream. When Webb's Pluto findings reached NASA headquarters, excitement quickly gave way to caution. The data contradicted long-established atmospheric models, and within days, internal memos began circulating with titles like Atmospheric Anomalies, Pluto, and Triton Comparative Study. Some reports vanished from public databases, others were quietly reclassified. Those who had worked directly with the MIRI instrument noticed strange omissions in the released datasets. Entire lines of spectral information missing, marked as instrumental noise. But buried in one of the surviving technical drafts was a single unsettling sentence: observed non-thermal infrared emissions inconsistent with radiative equilibrium models. In plain English, Pluto was breaking the laws of energy balance. Then, another layer emerged. A secondary analysis detected weak electromagnetic activity above Pluto's terminator line, the boundary between night and day. The pulses were faint but unnervingly regular, repeating in intervals too precise to be natural. Initially, scientists thought it was auroral activity, maybe charged particles from the solar wind. But one notation in the confidential appendix changed everything. Haze particles exhibit properties consistent with conductive microstructures. Conductive, capable of carrying current. If true, it meant Pluto's sky wasn't just chemical. It was electric, behaving like a global circuit. Its haze wasn't only radiating energy, it was channeling it, distributing power through invisible filaments like wiring across the planet. Suddenly, the mystery of Pluto's cooling deepened. The question was no longer why it was losing heat, but what it was doing with that energy. And when Webb turned toward the planet's night side, the answer came in the form of a light no one expected to see. When the James Webb Space Telescope focused on Pluto's dark hemisphere, scientists anticipated emptiness. No sunlight, no reflection, just silence. Instead, they detected light, faint, rhythmic, structured. At first, it was dismissed as noise or reflected glow from Charon, but the geometry didn't match. The pulses repeated every 247 seconds, perfectly timed, perfectly consistent. The pattern was identical to a mysterious cosmic pulse Webb had recorded months earlier from deep intergalactic space. The realization hit like a thunderclap. The same frequency observed billions of light years away was now emanating from Pluto itself. NASA ran a spectral decomposition to decode the signal. What they found was mathematically impossible. Each pulse contained micro-variations in amplitude that, when plotted, formed numerical ratios. 1.618, 3.14, 2.718, the golden ratio, pi, and Euler's number, the constants that describe the architecture of the universe. It wasn't noise, it was information. Webb's spectrometer traced the source not to the atmosphere but to something buried beneath Pluto's ice, a reflective layer nearly 12 kilometers below the surface. It wasn't rock. It wasn't water. The spectral signature was metallic. The shape, determined by radar echoes, was almost perfectly spherical, a structure spanning a third of Pluto's diameter. For decades, scientists had believed Pluto was geologically dead. Now, it appeared to be harboring something built. Vibrations synchronized with the infrared pulses suggested movement deep within the crust, rhythmic, deliberate, like a machine operating under the ice. One researcher at NASA's Goddard Space Flight Center whispered, "It's like the planet is trying to speak." Within weeks, the data was classified. Officially, NASA attributed the readings to resonant particle scattering, but internally, panic spread. Several scientists resigned after being asked to sign non-disclosure agreements regarding Webb's Pluto data. Anonymously leaked notes from one of them contained a single haunting line: "Pluto is not what we thought it was. It's something built." Since then, the faint pulse continues, sometimes weaker, sometimes stronger, repeating across the void as though aware it's being watched. Webb still detects it occasionally, hidden beneath cosmic noise. Every time it whispers the same mathematical constants, the same silent code written into the bones of reality. The question is no longer what Pluto is, it's who put it there. So if this story made you question what NASA truly knows about the outer solar system, don't look away. Subscribe to this channel. We uncover the discoveries they don't want you to see. Turn on notifications, because the next time the James Webb Space Telescope looks back at Pluto's frozen heart, the universe might just answer.